Hey there, everyone. Thanks for joining us for another edition of National Museum of Industrial History's Virtual Museum. If you caught us the other day, our historian Mike Pearson was talking about the iconic steel stacks and blast furnaces right outside the museum and what they did and how they produced for Bethlehem Steel. And today we're going to be talking about the blowing engines that powered those steel stacks, another very important part of the process. If you've ever been in the museum, been to the Hoover Mason Trestle and seen those giant turbines and engines, you might have wondered how they work. So today we're going to be covering that with Mike. And we also have a couple of other talks coming up soon. This Friday, we're going to be joined by Richard Hall, who's calling in from New York City. And Richard just authored a book about John Roebling. This is another follow-up talk. If you caught the talk on Washington Roebling, who is an engineer and built the Brooklyn Bridge, this is about his father who originally started that project and had passed away before he completed the bridge. So Richard did the first biography about John Roebling in 75 years, and he'll be joining us in just a couple of days for a talk and presentation about his book. And we also have some kids programming coming up that we're launching. If you'd like to check out more about those programs and other programs that we're scheduling out for the next couple of weeks, you can visit our website at nmih.org or stay tuned here to our Facebook page as we post new programs. If you're watching this live or joining us afterwards, you know that you're watching this for free. You don't have to pay anything for it. The museum is closed right now, so we're not getting any revenue in. So if you're able to, we encourage you to either donate to the museum, get a membership. There's a couple different ways that you can support us. And there's a list of those ways at our website at nmih.org. We'll also be putting a comment down in the link down in the comments below. Today, again, we're joined by our historian, Mike Pearson. He's been with the museum in some capacity for over 17 years now. He's a graduate of both Moravian and Lehigh, right by the museum. And he's been key into the interpretation behind all the artifacts at the museum. And he's been on the site at Bethlehem Steel for many, many years and is very intimately knowledgeable about the machines that are on the site, the buildings that are there, and the blowing engines that he'll be talking about today. So if you have any questions, please leave them in the comments. We'll be watching them live and sending them over to Mike, or we'll be saving them towards the end of the presentation, so stick around for a Q&A afterwards. But thanks again, Mike, for joining us. I'm going to pass it over to you for the presentation.
Thank you for having me. I'm going to switch screens so we can see a slideshow with some images here. This should be popping up momentarily. So the first thing I want to show you is really the earliest form of blowing engines. This presentation is really about moving air into furnaces. So what we see here is a very early furnace on your left, very typical of what you'd find in the colonial era in the United States, really all over the world where they were making iron. And then the method for blowing air into it. Think about how you blow air into a fireplace. You take a bellows and you pump it up and down with your hands. And the bellows blows the air wherever you direct it, which is usually into the fire. So they did the same thing here, just mechanically. They have this giant bellows, looks like it's 6-8 feet tall. And then they have a water wheel. And then the water wheel has arms coming off of it. The arms push down on the bellows, pump the air into the furnace. And then you just keep on repeating that process over and over again, day and night, for weeks, months at a time. And that's how you feed air into the furnace. So this worked great for smaller furnaces and furnaces that were located near sources of water. But once the furnaces started getting bigger, you had to really figure out how do you make this more economical? How do you manage these resources? So as the furnaces got bigger, if you had enough water, you could just add more water wheels. So this one shows a wider water wheel and looks like multiple blowing tubs there. That's what they call the cylinders that actually do the compressing of the air or pumping of the air. And these days it was colonial era, again, it was very low pressure. So you have, again, those crank arms extending off of the water wheel and then driving rods that go up to crossheads that take the crank motion and turn it into up and down motion, just going reciprocating in and out, driving a piston up and down inside the cylinder. Air comes in one side, gets pushed by the piston, it leaves out the other side, and it goes to the blast furnace from there. Very, very basic and simple operation. This is what one would look like in practice. This shows the blowing apparatus at Hopewell Furnace. You can actually go there to, again, when the virus is over, and actually see this in person. You can see the water wheel driving those elevated tubs up there, and then that pipe in the upper top of the photograph connects the blowing tubs to the furnace. So as blast furnaces evolved and got larger, and in other cases just kept on running and running and running, and having to face competition from new producers, management looked at ways of improving efficiency. So one of the ways of doing this was by converting from water power to steam power. Water power could be unreliable if you had a drought, or if you had some other use for the water. But steam engines could take a relatively small amount of water, boil it, convert it to steam, and then the steam would actually be used in the engine to propel the furnace, to propel the blowing tubs, which would provide air for the furnace. So this is an example from Cornwall Furnace. That was a colonial era furnace that had been around for quite a while, but they upgraded it in 1841 with the steam engine built by West Point Foundry. So what they did, instead of putting a whole brand new system, at least they made a whole brand new design in, they took the steam engine, extended the crankshaft through the wall, and geared it to a set of blowing tubs that look a lot like what you saw in Joanna Furnace. So you have this basic 18th century technology that was just enhanced a little bit. And that served this furnace into the 1880s when it was shut down. So again, you can see that same basic wooden blowing tub apparatus up there that pumped air into the furnace. But you can imagine with the machine made of wood like this, the pressures were fairly low, and the furnace that was driving was only a few dozen feet high. As furnaces got more advanced, they had to get air in that higher pressure to keep up with the competition. So what you see here is the next step of blowing engine design, where they got away from that colonial era wooden blowing tubs and water wheel setup and regular steam engine. That's fairly, as far as steam engines goes, not too different from a standard design of an engine. You could make the flywheel a little bit different on that thing and belt it up, add a governor to it, you name it, and it would really function like in any factory setting. But what you started seeing in the mid-19th century was engines really designed specifically for blowing purposes, with the tubs integrated into the engine design. You can see one of these furnaces here at Carrick Furnace in Meadow, Pennsylvania. For those of you watching, you probably heard about the East Broadtop Railroad. This is really not all that far away from there. So if you're heading out in that direction, it's worth looking up Meadow, Pennsylvania, and you can actually see this from the side of the road. So they had an older charcoal furnace that they wanted to keep running in the 1870s. So in 1879, they purchased this blowing engine from Weimar, which was a company that specialized in producing these types of engines. So you'll see it's completely vertical in nature. That blowing tub, again, it's just like those colonial furnaces at the very top, but it's made of cast iron now. And the steam engine was directly connected to it with a piston rod that went from the engine cylinder, which was at the bottom of the blowing engine, straight up to the top. And there were a crosshead that would drive a pair of flywheels down at the bottom. They're a bit obscured by the weeds, but you can just barely see one poking out there. But this design lasted for decades, the general arrangement at least. So we can move on to see what was common in the 1890s. And actually, along the way, I forgot about this image. This is another variation from that same manufacturer. Let's put the steam engine horizontally, and then they added they added a second blowing tub, connected them on the outside of the flywheels. And this is a very common type of blowing engine from the 1870s, 1880s era. Now in Bethlehem, the first blowing engines were built by the Bush Hill Iron Works in Philadelphia, but by the 1870s, Bethlehem had advanced to the point where they had their own foundries and machine shops, and they were in a place to build not only their own engines, but furnaces and buildings from the ground up by themselves. So Chief Engineer John Fritz, as he was planning the new pair of blast furnaces, number 5 and 6 in the 1870s, decided that he was going to take a crack at establishing his own blowing engines. So this is a cross-section view of one of the engines that he built. And these engines, they were criticized in their day, but they did prove to be very reliable. They actually ran for almost 50 years. And coincidentally, the day that they were shut down for the last time was the day that John Fritz himself died. And they were not shut down because they were worn out. They were continuously maintained, but they were shut down because they were lacking in efficiency compared to much more modern technology. When you look at period literature from the time these things were replaced, they were wondering what's going to come around in 10 years. Would it be gas engines, turbines? What was going to be the thing that would supersede the technology that was replacing these things? And they figured that no matter what they did, the machinery was going to be so well built and maintained that it would be as good as new the day they took it out of service. And that would only be happening because something better came along. So what we notice about this engine compared to the other ones is this engine has a much larger flywheel that helped it maintain momentum much better. And the engine itself is off on the right. The blowing tub is just to the right of the crankshaft in the middle of the flywheel. And again, it's a fairly simple construction. Piston rod goes from the engine to the blowing tub, and it moves that piston back and forth all day long, pumping air into the furnace through the stoves. What made this engine unique, though, is that compared to those earlier engines, which were all single cylinder, this one is 2 cylinders. You can see it right here. Small cylinder, this is on the left-hand side of the photograph I'm looking at. Small cylinder on the right, big cylinder on the left, joined together. And you can see faintly the big blowing tub behind them. This is a compound engine, so the steam gets used in the small cylinder, and then it gets piped to the larger cylinder used the second time. It's the same basic process that the coreless steam engine in the museum today uses. So as we move on, we'll start seeing what other companies were doing. John Fritz had a vision of doing things his own way. So his blowing engines were really never duplicated. What happened commercially in the rest of the country, for the most part, was you took that design we saw earlier from Metal, Pennsylvania with that vertical engine, and they just made this bigger and more powerful. So this is an example from Station Square in Pittsburgh, Pennsylvania, where you took that same basic situation where you have the engine at the bottom, cylinder at the top for pumping air, and just made it much more larger and more efficient. And they did that getting efficiency by using coreless valve gear. Again, the same type of valve gear on the big steam engine inside the museum today. The coreless valve gear allowed the engine to have a much lower fuel usage rate, which was important in the steel mill because they were burning blast furnace gas, which is a byproduct from the furnace under boilers to make steam. And the less steam they could send to the engine meant more steam available for other purposes. So you can see pretty clearly here, you got the steam cylinder on the bottom, the cross head that goes above the flywheel, and then rods extend down below that to actually rotate the flywheel. And all the flywheel does is maintain momentum and keep the engine run smoother. Because if you didn't have that flywheel, this would be just strictly reciprocating motion, starting and stopping. The flywheel helps the engine spin around much more freely and carry it past those dead spots at the top and bottom of the stroke. Just a few more views of this engine. This thing is really massive. I think the flywheel's somewhere in the neighborhood of 16, 18 feet in diameter. And when these were set up in a furnace situation, you might have one for a very, very small furnace, but typically furnaces were built in groups 2, 3, 4, 5. Bethlehem even had visions of 8 furnaces on their planning books at one time. So these engines would be installed in rows. This is down at Sloss Furnaces in Birmingham, Alabama. They have a 1902 engine house with vertical steam engines. Slightly different design, but same basic setup with the steam cylinder at the bottom. You can't even see it because it's hidden inside the frame of the engine. Connecting rod going down to turn the flywheel, which is also partly below floor level. And then the actual blowing cylinder at the very top. And then you can see that the air from that cylinder would be pumped into the piping network, the cold blast main. And that would take it to the stoves where it would be warmed up and then to the blast furnaces. This is just another view showing those engines all in a row. One of the advantages these vertical engines had is it saves a lot of space. If you compare how big this building is compared to the engine house in Bethlehem that survives today, you'll notice it takes up a much less real estate. The flip side of that is it also makes the engines much more difficult to work with. So if you have to go and do a repair, you have a lot more difficulty in getting access to those parts. Now we're skipping ahead a little bit here, but since we're still talking about steam engines, this is a good point to introduce what ultimately ended up surpassing the actual engines themselves. When you think about engines, you have all of these reciprocating parts moving up and down, starting and stopping, and the complicated valve gear mechanism to control the timing of when those events happen. But if you can have a steam-powered turbine blowing the air, then your operation gets a lot simpler. In the early days, these really weren't cost effective, but as they got much more powerful over the decades, they eventually became the industry leader and are in use at the blast furnaces that are still in use today. So what you see here on the right-hand side of the image is a steam turbine, and on the left is the actual blower mechanism. This is again at Sloss. You can see the turbine's been lifted up, so you can see the turbine blading exposed. The steam would actually go in, hit one blade of the one set of the turbine, exhaust into the second series of blades, and on and on and on. So that steam would get used multiple times. The device you see at the very top is a governor. And this is what the turbine rotor looks like from the Bethlehem turbo blowers. There used to be 3 of these in Bethlehem. We'll hopefully discuss those a little bit later, so they make sense in terms of Bethlehem's evolution. But that's what's left of one of the Bethlehem turbines. This is the actual blowing end. Notice you'll see a good local name on that, Ingersoll Rand. They built a good number of these turbo blowers. One of their primary businesses was making machines for compressing air. And these turbo blowers basically did the same thing. The boundary line between, traditionally at least, when you say something's being a compressor versus a blower is about 30 pounds per square inch. So in the mid-20th century, you're getting blast pressures up to about 30 psi. And even at lower pressures, the same basic technology of compressing air is what you're doing, just you're emphasizing volume over pressure with these types of engines. So this is a look inside that turbo blower casing. You can see 1, 2, 3, 4 units in there, and they pick up the air, spin it around, pump it out the other side at a high pressure. And these things could get up to some really impressive numbers of cubic feet per minute. Like the Bethlehem turbines, they could do well over 100,000 cubic feet a minute. So to put that in perspective, the average person breathes about a little over 1/4 of a cubic foot of air per minute. So we'll keep that in mind as we go down and hear about some of these figures with the engines themselves later on. This is a view inside the Bethlehem Powerhouse. They had 3 turbines that were added in the 1940s and 50s. We don't have a huge amount of images from it, so this image actually shows it when the Lehigh River flooded, which is really what they were documenting, and showing it how it impacted powerhouse and plant operations. And as I mentioned, these things are really the mainstay of the modern blast furnace blowing plant. So this is a shot from a pair of turbo blowers at Wheeling, Pittsburgh, Steubenville, Ohio operation. It's been demolished, but you can tell that these were maintained and operated well into the modern era. In another view, and again, you can see that these turbines take up a relatively small amount of space compared to the engines that we're going to start seeing momentarily. Now, one thing that's important to note about those engines, they run on steam. Same thing with the turbo blowers you just saw, but the steam has to be made somehow. It comes from gas, which is a byproduct of blast furnace operation. The gas is mostly carbon monoxide, and you can see in this chart here about raw materials going into the blast furnace. You have almost 2 tons of ore, a little over a ton of coke, and almost 5 tons of air that gets pumped into the blast furnace to make a little bit over 1 ton of iron. So when you look at all of that air that's flowing into the furnace, you have to look at what's coming out of it, and you're getting well over 13,000 pounds of gas associated with every ton of iron you make. That gas is mostly carbon monoxide. It has a BTU value of about 95, 100 BTUs. That's British thermal unit. It's a means of measuring how potent the gas is. So for comparison, natural gas is a little bit over 1,000 BTUs. So even though this was only 1/10 the heating value of natural gas, you have so much of it that if you can harness it and use it, you basically get free fuel. So when Bethlehem Iron Company and Bethlehem Steel was trying to figure out how do they deal with the expansion plans and fuel the plant, they were looking at their boilers for their steam engines at the time, and they realized that some of the steam was coming from coal-fired power plants, and they were spending, I think it was upwards of $1 million a year on coal. But if they could harness that blast furnace gas a little bit better from their bigger furnaces that they're planning to build, they could put that blast furnace gas to use, not in boilers that would inefficiently convert the energy to steam, but take it directly to the engines. So they started looking at what the Europeans were doing because fuel costs in Europe were much higher at the time. So the Europeans were a little bit further ahead in their development of gas engines that could utilize blast furnace gas as a byproduct from the furnace. So they looked at some of the leading examples in Europe and found a Nuremberg design of engine. And they decided, along with a lot of other steel companies in the United States, that this was really the way to go. If you think about your automobile engine, this is really comparable to a 4-cylinder car engine. It looks a lot different, but it functions in the same basic fashion. Instead of having 4 independent cylinders, this has 4, they call them cylinders, arranged, and this gets a little bit confusing, but for practical purposes, 2 double-acting cylinders. So this is an exploded view showing how you would pull the parts out for installation or repair. But you have a cylinder on the left, one in the middle, and then you have your crankshaft on the right. The piece with the grooves in it, you can see there's 2 that are mirror images. Those are the actual pistons. So because you have 2 double-acting cylinders, you can have a 4-stroke engine like your automobile, and you'll have a power stroke on every single stroke. If anybody has questions about that, let me know. We can explain 4-stroke cycle in theory a little bit deeper. But basically, if you didn't do this, you would have 1 cylinder making 1 stroke, and then you'd have to let the flywheel revolve 2 times before it could come back and start the process over, because you have to suck gas in, compress it, ignite it, and then exhaust it. So that's your 4 cycles. So if you can have 4 times where this is happening, 4 places this is happening on the engine, then there's always one of those places where it's going to be firing and actually making power. So Bethlehem was not the first company to build these engines in the United States. There were actually several. Sorry about my computer freezing again. This is an example from Mista Machine Company out in Pittsburgh. You also had Westinghouse and a number of other places manufacturing these engines. And everybody had a slightly different design. If you look at this compared to the Bethlehem engines, you'll see that the blowing tub is on the end here. Then you have the 2 gas engine cylinders, and then the crankshaft. This made access to the cylinders a little bit more difficult than it had to be. But it might have saved a little bit of space. So there were always trade-offs that you were looking at in producing these engines. This is United States Steel Gary Works. You can see the men here in the process of setting up their blowing engines. These ones are much more along the lines of the Bethlehem engines, but again, built by a different manufacturer. And you can see that these powerhouses were massive. Back when they were first built, they were figuring one furnace would require 2 engines to supply the air to it. And then for every 4 or 5 furnaces, you would have a spare engine. because there was inevitable at some point one would break down. You'd have to do routine maintenance, like changing the points, or in later years, the spark plugs. So you always try to keep a reserve on hand. This is just another view of showing how large these places could be. When you have several furnaces, these powerhouses really started lengthening almost to the point where it's hard to see the end of them and hard to count the engines. Bethlehem at its peak had 17 blowing engines, all at the same time. This is where the building is actually located at, for those of you not familiar with the site. You have your blast furnaces on the right, your ore delivery trestle in the middle, and then your blowing engines on the left. So you want to have these things as close as possible to the furnace to reduce the amount of resistance in the pipes that the air travels through from the blowing tubs of the engines to the stoves and furnaces. So this is a drawing showing what it looked like when they were getting ready to install the turbo blowers. What you can see here is what Bethlehem had in the intermediate years between Fritz building his engines and these big giant gas engines getting installed. In 1907, they installed 3 Southwark steam-powered blowing engines. They had horizontal steam cylinders and vertical air cylinders, and those things lasted into the 1940s and 50s. They were gradually replaced by the turbo blowers, because when you look at the mathematics behind it, there was just no competition between these engines and the much more modern turbos. You can also see that they were in a much narrower space. The circles, hopefully I can zoom in on them, were for blowing tubs that were vertical, so they didn't need as much of a horizontal footprint. So this building was actually narrower. And after this engine was taken out, you had the turbos take their place, which were even smaller than those engines. But you can look on the left and see another gas engine powerhouse that made electric power, but the same basic design of engines. You can see the footprint is much, much wider. And the footprint is actually a big deal in these engines. In Bethlehem, that design just barely worked. They were able to come fairly close to the railroad tracks, but not interfere with them. But in other facilities, they actually angled the engines to make them fit. This is a drawing showing the layout of the foundations for the engines that currently exist. The first part of the building that exists today was about 100 feet wide and 310 feet long. That was constructed in 1910 and actually put into service in 1911. Had 5 engines initially, and then they added more over the years. One thing that you can note in here, and we'll talk about this later, is the exhaust gas tunnel. The engines today have individual stacks, but there used to be a tunnel that funneled the exhaust gases to a central stack. A few more architectural drawings showing the width of the building, how it's constructed. And again, that placement against the furnaces is key. You can see 1, 2, 3, 4, 5 big pipes on the outside of the building. Each one of those pipes goes to a blast furnace, and those pipes are what carry the air from the blowing engines to the furnaces. And the building was absolutely beautiful, and to this day, it still is. Brick construction, windows, it was very bright on the inside. It was actually illuminated from both ends of the building. And white tile on the inside. It was really, really, really classy. And it had a sister building. We hopefully can talk more about this at another time, that made electrical power with the same basic types of engines. And this one even had a very nice concrete sign cast right into the building. It said gas engine powerhouse. And when this building was demolished, the concrete piece here was actually salvaged, and we have it in storage for the museum today. So we'll do a few more exterior views just to get a sense of what this place looked like on the outside. You can walk by it today, but the landscape it worked at in the plant was very different. You were hemmed in by buildings, railroad tracks. It was not uncommon at all to see trains parked in front of these places. Because this is, again, the AC powerhouse, but it's almost a clone visually of the blowing engines, which you can see back in the distance there. If you're looking at old photographs, you can tell the difference between them, because there are 7 AC engines, and they all had waste heat boilers, which were these boxes outside the buildings, whereas the blowing engines, there were 17 of those. and only 4 waste heat boilers associated with the more modern engines. And then between them was this narrower section that had the Southwark steam engines, and in later years, the turbo blowers. So again, Bethlehem had a tradition of building things themselves. So when it came time to invest in gas engines, they thought about it and decided that why buy from another company when they had the facilities right here in Bethlehem to build their own. So that's exactly what they did. They had foundries within an air shot. The building that used to house the Bessemer converters by this time was doing iron castings. Number 4 machine shop, I believe it was one of the machine shops directly nearby that foundry. It's gone today. Was in a position where they could actually do the machine work on these. Number 2 machine shop did repair work for them. And you could actually build and maintain these things right on site. So this is a photograph taken as one of the engines was under construction. You can see they have it up on stands as they're in the process of test fitting everything together. And you can also see a cylinder for a second engine in the foreground and other components scattered around. We're going to move now into the actual engine house itself and start discussing how these things actually worked. So this is a view of those first 5 engines that were installed and actually got put in service in 1911. You can see the building gets narrower, and then there's a bunch of other engines in the background. Those were electric generating engines from a slightly earlier time period, and those eventually got torn out. And the Bellowing Engine house expanded, and the current engines replaced those engines. Then you have the Southwark steam engines, those vertical horizontal engines. I'm trying to zoom in on that image so you can see them better. Well, it's not letting me zoom in, but anyways, in the far back of the photograph, you can see those flywheels, and there's a vertical component there. Those are the blowing tubs for the steam blowing engines, and that's about the spot where the overlook exists today on the Hoover Mason trestle, where you'll be looking into the Bellowing Engine house that has since expanded into that direction. So Bethlehem didn't build engines just for the Bethlehem plant. They also built them for the Maryland Steel Company, which eventually became a wholly owned subsidiary of Bethlehem Steel, which was their Sparrows Point plant. They built them for the Lackawanna plant, and several other installations throughout the country. So the way these engines work is they're horizontal engines, and the parts inside them are so heavy that instead of the piston carrying the entire weight inside the cylinder, they actually have a piece that comes out called the tailpiece that rides on the slipper on a track or guideway that takes some of the weight off. They have a second one of those hidden away in the middle of the engine. Then a third one, which is, you can see a spare example here labeled crossfed, connects to the piston rod on the right. And then at the top and bottom, there's holes for additional rods that connect back to another crosshead, which then at mirror image feeds into a piston rod and piston for the blowing cylinder. You can see air intake is up on the top. And I wanted to throw this in just so you guys can read it momentarily. But this is a page from the manual that shows the engine sizes, gas engine cylinders. There are 42-inch diameter on the smaller engines, up to 47 inches in diameter on the big engines. And again, this is because they were burning blast furnace gas, which had a relatively low BTU value to it. If you were burning natural gas that was much more potent, you could have a smaller cylinder and get the same amount of power. But with the blast furnace gas, you had to have a larger cylinder to get the same amount of energy out of it. They're rated in cubic feet per minute, so the smallest engines were about 13,000 cubic feet per minute. And if we go back to our example of how many cubic feet a minute a person blows, which is a little over a quarter of a cubic foot per minute, it would require about 48,246 people to equal the capacity of the smallest blowing engine. And if you think about a hot air balloon, those an average size hot air balloon might have 65,000 cubic feet of air inside of it. So a small blowing engine would take 5 minutes to pump that much air, but one of the larger engines in Bethlehem would only take a minute and a half to do the equivalent of filling up a hot air balloon. So these are drawings. I apologize for the quality. These were just reference shots so we could see what they look like. When we get back to the archives someday, hopefully we'll be able to do a more proper scan of these. You can see how the engine actually works on the inside. We talked about the piston rod and the piston. You can see those here. But if you compare these to a standard internal combustion engine like in your automobile, you notice something very different. They're hollow. This is because the temperatures were so intense that these things actually had to be water cooled. And same thing with the cylinder itself. We'll see it in a color-coded drawing a little later, but the cylinders have a water jacketing around them. Up at the top, you have your air intake. That's a little bit better seen in this image here. So the cylinder is down at the bottom. We're moving on the left-hand side of the image. You'll see this slightly convex valve down there. That's actually a poppet valve that moves up and down. And that's what seals off the cylinders from the airflow. Then you have a series of springs up on top. And then there's an arm at the top that gets activated to push that valve down. So when that valve comes down, it brings in a mixture of air and gas. We can zoom in here and see how that air and gas actually comes in. The gas is piped in from the basement, and that's a very dangerous place to be. If there was ever a leak, you could get overcome by carbon monoxide pretty easily. So if anybody ever had to go down there, they worked on the buddy system in case somebody didn't come back up. They could run down for help. It goes through valves, and then it gets mixed in the chamber up here, and you have a sleeve valve here that rotates around. This is a very interesting situation. The sleeve mixing valve has these spirals cut into it, and as the engine throttle operates, it twists this sleeve, which is aligned vertically, back and forth, and that adjusts the proper automatically adjusts and maintains the proper proportion of air and gas mixture. And you can throttle it up and down depending on what your load was like. Even though these engines had to run basically continuously, the furnaces themselves didn't always need the same amount of air. If you were going to be tapping the iron out of the furnace, you would want to have less air blowing, so you're not having a rush of air pushing that iron out. You wanted to have that much lighter, so the engines would sometimes have to be throttled back. So by twisting this valve, you can control the amount of fuel and air that comes into the engine. And then as the valve itself moves up and down, that actually does the admission. And then there's a similar setup, but without the twisting sleeve at the very bottom for the exhaust valves. This is what it looks like looking down into there. So you can see the different passageways where the air and gas would come in. And these are some of those sleeve valves that would actually twist back and forth, depending on how much fuel and air you needed to mix into the engine. A shot of the exhaust valve looking down, and you can see again how beautiful this engine house was. Even in the pits underneath the engine, they were lining them with red quarry tile, and it looked beautiful. Up until the late 20th century, this was a place where you could go in, and multiple people have said you could eat off of the floor of this building. They had mop stationed by the engines. The brass was polished. These guys really took a lot of pride in their machinery. And when the president of the company came to visit, this is one of the places that they would show off to him and to visitors. This is just another example of showing that cutaway of how the fuel and air came into the engine. The exhaust valve is a little bit more visible here. You can see the eccentric shaft alongside the engine. Just like the coreless steam engine we have, it has eccentrics. You can see it in the lower left here. They revolve around a shaft and provide a linear motion from the straps around them that open and close the corresponding valves. The cylinders themselves are very unique too. You'll notice that this isn't one cylinder. Well, the cylinder isn't made from one casting. It's made of multiple pieces. You have your front, your back, and there's probably different technical terms for these, but this is easier to explain in this image. And then this piece that clamps down around them. So when you look at that in cross section, you can see you have your left and right pieces, and they're joined together in the middle by prisoners or dog bones, depending on who you're talking to. These are pieces of steel that have been heated up, put into place, and shrunk down. And as they shrink, they bind this together very, very firmly. these castings were subjected to such tremendous temperature differentials that they actually made them out of steel. And then only the actual cylinder liner, which is the tube inside the cylinder castings, was only made from cast iron. And then you can see that the piece that clamps around it is the gas passage, and to the left and right of that, you have a hollow space, again, inside the cast iron cylinder halves, that's filled with water to keep the engine cool. This is what some of the pistons look like. They actually have a rack full of spare pistons in the Bellowing Engine house. And then the pressure inside the engines was supposed to be about 350 PSI, that's pounds per square inch, as the explosion occurred when the gas was ignited. If the pressure got a little bit too high, then this safety valve up here would go into action. The valve would open up against the spring, and the excess pressure would be released into the room there. Now, the exhaust temperature was so intense on these things that you could actually take the exhaust at 1250 degrees, and on the larger engines, run that through waste heat boilers and make steam. So between the 4 boilers here and the 7 boilers with the electric generating engines, they actually made 8% of the plant's steam needs. So that was very helpful in running turbo blowers and other steam-powered devices. And again, saved a tremendous amount on your fuel bill. And when you looked at the efficiency of these engines, the gas engines operating by themselves were about 25 to 30% efficient. But when you added in these waste heat boilers, then you got an efficiency of around 50%, which was really, really good even in this day. So after you get the reciprocating motion from the pistons, you have your crosshead that takes the motion to a driving rod, which spins a crank. All of this stuff is enclosed in shrouding, so it's a bit hard to see. But whenever volunteers, Rick Rowlands, crawled inside there, this is probably 10, 11, 12 years ago, and you can get an idea from him just how big that crank is by how it dwarfs him. These engines have a 60-inch stroke, so that means every time the piston fired, everything inside moved back and forth 5 feet. Between the motion and really the heat, these engines also were mounted a bit differently than other ones. So this casting that he's standing in the frame of the engine is bolted down and anchored all the way down in the foundation over 12 feet deep, and deeper below that with the concrete still. So those anchor bolts hold down the frame of the engine, but the actual cylinders are sitting on a track so they can actually move linearly and expand. There wasn't a whole lot of expansion, but it was enough that if they were bolted down, you might actually break the bolts or do some sort of damage, but they wanted the engine free to expand because it grows. The early engines were single engines. That means you had your gas cylinders, your air cylinder, and a flywheel. So you had one engine and one flywheel. They thought this was a very logical way of going about it. It saved on cost for producing the pieces, but these engines only had about 1,500 to 1,800 horsepower. They were very happy with that in the early years, but by the time the 1920s rolled around, they realized that if they could build bigger engines with bigger cylinders and combine 2 engines into one, you could reduce the 2 flywheels into 1 flywheel and have what they call twin engines, where you have a left-hand and a right-hand side engine all tied together by a common crankshaft. So we talked about the actual power of the engines. Now is a good time to talk about the air. If you're on the Hoover Mason trestle, you can look up at the eastern end of the engine house and you see this big thing that looks like a smokestack. That's not a smokestack. That's actually an air intake stack that was located as far away as they could reasonably get it from the blast furnaces. Because again, even with all those dust control measures, there was still dust and you wanted that air to be as clean as possible. So this stack took the air and funneled it into the basement of the building. And from the basement, it rose up and came up through these passages. You can see it behind the caution tape, and into these valve cages where they had little valves that fluttered back and forth and let the air into the blowing cylinders. Now, they had to constantly monitor the temperature of the air being pumped out of these cylinders. That's why they have these thermometers here. In the early days of the plant, this was easy to do because you had a lot of workers in there. But by the 1990s, you were only running one blast furnace, so you only needed a handful of people to operate a minimal amount of equipment. You might have only had 2 guys working there. And by this time, the blowing engine house with the reciprocating gas engines was 540 feet long, plus an extension on for the turbo blowers. If you only had 2 guys in the entire building, then odds are you're not going to be able to keep as good an eye on things as you might want to. So when you compress air, the air heats up. And if you compress the same air, the heat keeps on building up and building up. So if there was a malfunction and you weren't watching that temperature gauge, the thermometer there, the temperature of the air could actually get to such a point that the lubricating oils left over would actually ignite. And that's what happened in 1993. They had a fire in the cold blast main, which for practical purposes really amounted to what I would call an explosion, even though it was technically a fire. And that blew out some fittings, valve on top, and did some other damage. And you can still see that from the Hoover Mason Trestle today when you look into that blowing engine house. So after they had compressed the air, it was sent into an air reservoir tank and then through what they call a Dibley valve. This was named for the chief engineer of the Joliet plant of the Illinois Steel Company, who invented this special valve that would automatically lift up and pump air into the mains going to the furnaces. But it was also designed in such a way that if the engine shut down, the valve would automatically close, and it has a counterweight on it, which was positioned just in the right place so that the valve would descend slowly and not come crashing down. And this was important with the engines because if you had to close the valve off by hand with an old-fashioned gate valve, that would take quite a long time. And you actually run the risk of having the air as the engine slows down come back in from the other engines, push the engine backwards, and have some disastrous effects. So after it lifted that Dibley valve, it went into the manifold here. You can see 1, 2, 3, 4, and there is a 5th on a lot of these. These are valves that take it to the various furnaces. So you could actually have any engine blown by any furnace blown by any engine. So it gave you a lot of flexibility there. And of course, at the other end, you have these blowing pistons. They're about 72 to 84 inches in diameter, depending on the engine. And again, they had this cross slide on the back, the slipper that would allow you to take some of the weight off of the actual piston and reduce the amount of wear on it. So these early engines, 1911 versions, the singles stayed in service until the very end, but in 1927, they expanded the engine house and put in the twin engines. So you can see in comparison to the singles, they had 2 flywheels, really one for each engine, just side by side, mirror images of each other. You have the twins, which have 1 flywheel. And by the time you added in the larger cylinder diameters, you're looking at about 5,000 horsepower coming out of these engines here. This is a view taken from the overhead crane looking down the engine house. Again, at the peak of operations, they had 13 single engines and 4 twin engines for a total of 17 engines. This is where the operators worked out of. This was located in the center of the building. In the 1970s and 80s, they started doing what they called harvesting the plant when they realized they had excess pieces of equipment. Because again, this was a slow end to the plant. They didn't just shut it all off like a light switch. They started turning off the first furnace in 1960 and gradually turned things off as needed from then. So they actually took some of the engines out. So there's still 12.5 engines left in there today. But in some of the spaces, they used it for part storage, the shanty here that the workers worked from. And the workers' jobs, they had a variety of tasks. But we're going to look at the guys who actually ran the engines and what they had to do. These engines weren't like your car where you turn the ignition key and it turns a starter motor. These things were started by compressed air. They usually use plant air because the plant had a network of compressed air servicing it as a utility. About 200 PSI in these, for these engines was needed. And the air would get pumped into the engine cylinder and give it a push. That would get the engine started rolling, just like your car engine would get started with the electric starter. And once the engine was rolling on compressed air, then they would open up the gas mains and turn on the spark and let the engine run as an internal combustion engine. This is a backup air compressor inside the blowing engine house for getting those engines started up. So if you're at the far eastern end and you look through the doorway, this is what you see. It's not actually a blowing engine, it's an air compressor used for starting the blowing engines. Then you can see the ignition system on the engines here. These things were so big that they had multiple spark plugs on each cylinder. They literally encircled the cylinder to have enough spark to ignite all of this low BTU gas. You can also see a valve seat grinder positioned up on top here. Maintenance was a never-ending battle with these things, but because they made this initial investment back in the early 20th century, if they were able to keep up with maintenance, then they were doing really, really well on their cost. Unfortunately, I don't have a record of this worker's name, but he's standing at the control panel here. These were shots by Joe Elliott. And you can actually see what the workers had to manipulate to control the engines. You can probably zoom in this picture a little bit easier than those ones. This shows one of the engines that had some restoration work done to it. And you can see this big valve here. This is for 2 single engines. So you have engine 10 on the right and engine 11 on the left. Blast furnace gas, which is the fuel for the engine. Compressed air to the right of that. What I believe is a quick starting valve for getting the air going. And then you can read the controls on the furnaces. Controls on the panel board here. You can direct air to the different furnaces you want. You can check your temperature for oil pressure, how much wind is coming out of the engines. So you can adjust it accordingly depending on what the blast furnaces need. And this is a good point to notice that these engines are in fresh paint, or at least these components of them. In 2009, we got permission to go in and do some restoration work on them. So their former superintendent, Jim Phillips, he's deceased now, but he worked there in the 1950s, actually saved a can of the original paint, had it in his garage and brought it back to us. We were able to match the color from that original paint because over the years, the engines have faded. And we were able to do some restoration work on engine number 11. At the time, it was felt that if the engine house was ever open to the public, that would be the logical one to restore because it was in the middle of the building. There was an open space where engines 12 and 13 had long ago been removed. This would be a good engine to showcase what it actually looked like when they were in their pristine, brand new condition. We also rigged up a chain hoist to it, 1-ton chain hoist, so we wouldn't do any damage to it, just a test. And we found that it was actually still loose. You can see we moved it a couple of inches on the slide. So these engines someday might still have some life left in them. This is the engine as we started with it. And then the finished product repainted in the Peplum engine green, along with safety yellow on the railings. And this is how the engine looks to this very day. You can see it from the overlook on the Hoover Mason trestle. Again, there were a lot of details that we didn't have time to cover. This is a topic that really deserves a book in its own right someday. If anybody has any questions, feel free to let us know. And if anybody worked on these, I know there's still some of you out there. We always love to hear stories, record them, and hopefully enhance this presentation and make this a more meaningful experience for the public over the years. Thank you for having me, Glenn.
All right, thank you, Mike. Jeremy asked, and thank you, Jeremy, by the way, he's a great photographer, for letting us use his images and promoting the talk. Jeremy asked, how loud was it in there when the machines were running?
This is one of those questions that really depends on who you ask. If you ask people who have a hard time hearing you, they say, no, it wasn't loud. You could have a conversation right next to them. And then you talk to other guys and they say, yeah, it was very loud. So I think the answer is somewhere in between. And again, it really depends on who the person was and what other experience they had. But you could definitely hear them. If you were living on Southside Bethlehem up on the mountain and you were trying to go to bed at nighttime, there are stories of guys who would open their window and hear the engines chuffing in the background and it would lull them to sleep.
Interesting. I don't know if you'll know the answer to this. Romano had asked, in the secondary operation of the blast air temperature chamber, do you know what the temperature was of the chamber converter?
Are we talking like the bustle pipe going into the furnace?
That I don't know. But Mike will also pop in the comments too and ask any questions that people might have. Sorry, go ahead, Mike.
I'll take a look at the question on Facebook later, and when I see it in front of me in writing, I can probably give a better answer then.
Gotcha. Taking a look, I think that's all the questions that we had. So thank you everyone who joined us. Again, we have a lot of programming coming up the rest of the month and into June. So please check out either here on Facebook or on our website at nmih.org. And also, if you're able to support us right now, there's ways to do that via either donations or purchasing museum memberships. And you can find that. There's a link in the comments here if you're on Facebook, or you can head over to nmih.org and find out ways that you can help support the museum right now and help these talks continue. Thanks again for everybody that joined us, and thanks for Mike for the presentation, and have a great afternoon, everyone.
Thank you.